Omkar Samane, and this is the Physics 1 Lab 2 motion of a falling object. To begin with, let's start with some important information. So a ball, which I took, was a crumpled up piece of paper and I dropped it. So an object was dropped from rest and the motion was measured using tracker. And the motion is then compared to two other computational models, one with just the effects of gravity and the other is gravity and air resistance. So a few fundamental principles that we need to know are Newton's second law, which is a net force is equal to change in momentum over change in time. The force of gravity is quantified as negative mg, and that's in the y direction. And we have drag force, which is negative b, magnitude of velocity squared, and this is in the positive y direction. So essentially what happens is that when an object falls, there is a point where the force of air opposes the motion, and something called terminal velocity can be reached, where the drag force and force of gravity are equal to each other in magnitude, which causes the acceleration to be 0 and the motion to be constant. So in this case, the net force is pointed downwards, and as mentioned above, the net force is equal to force of air, which is pointing upward, minus force of gravity, which is pointing downward. So therefore, the initial velocity is also equal to 0. So now let's look at the tracker data. So this is me dropping a ball, and it was measured through tracker. A series of about 15 to 20 data points were measured, and this right here is the time versus y graph right here. And I did put the coordinate system up here, which showed a negative position, a negative displacement, and I did calibrate it using this little poster in the back. So this did give us a bunch of data points right here, which were then used later. So next we have the predicted data, which is a force of gravity only. That is using this code right here. So I did Google the mass of a piece of paper, which I did find to be 0.0045 seconds, and then the initial vector is 0.001357. This is what I found through tracker, and the initial velocity is 0 since it's being dropped. So this g right here shows the force of gravity. And the j hat vector is where the ball is moving. Now this right here is extremely important, this b value right here, and this is the proportionality constant for the magnitude of drag force. So in this case, we're saying that there's no drag force, we're only just looking at the effects of gravity on the ball, and therefore we would put this b equal to 0. So now this all stays the same right here. I do want to mention it, line 72 and 74. I did update this to be final velocity is equal to initial velocity plus f net over m delta t. And same with the position, ball position is equal to ball initial position plus velocity times delta t, and it takes this velocity from line 72. So this program is run, and it shows us this wonderful parabolic trend right here, and these data points were then copied and used later on. Next, we showed the predicted data of the force of gravity and drag force. So everything honestly remains the same when it comes to the code, except for this value right here, which is a proportionality constant, which shows how much drag force, how much air resistance is present in the air. And this value just Googled as well. And everything else stays the same right here, and the program was run, and this causes a parabolic downward curve like this as well. All right, so now the data was then graphed and it showed this. So this does show some deviations, and I do think it's because of the coding, but this is the tracker data right here, and this is the force of gravity and predicted datas. So there is some deviation, and I think this is due to the fact of some errors due to improper tracking due to the tracker. But all in all, this lab does show the effect of Newton's second law, and especially in relationship to drag force and gravitational force. Now, to answer a few questions, which model predicts terminal velocity? It would be drag force and gravitational force both, and that's because terminal velocity is reached when the drag force and the gravitational force equal each other, and therefore causing no acceleration, constant velocity. And terminal velocity is when the object what is the terminal velocity? When the object is thrown downward, the velocity would still be the same, and this is because, again, the drag force and the gravitational force oppose each other at terminal velocity and create an acceleration equal to 0.